Okay, welcome back. We're going to start defining the atom now. And we're going to talk about the different experiments that were used to define the atom. So we're going to start with the cathode ray experiments. So a cathode ray tube is pictured on the left of the slide. And if you look at it, it seems to be this just empty tube, and it has some sort of a beam traveling through it, right? So a cathode ray tube actually applies an electric charge to a plate on the left. That's your anode, and then it travels across and past the screen into a receiver on the right. Okay, and that's the cathode ray. Um, and I'm sorry, it travels from the cathode to the anode. Anyway, so cathode rays are a stream of particles carrying negative charge. Those particles carrying a negative charge are known as electrons. So electrons were first discovered by Sir William Crookes, and these cathode ray experiments really helped us characterize these as being negative and as being a particle. And so there's some links also in your assignment. I want you to go check out a video of a cathode ray in action. You don't have to watch the whole thing, but if you do, the professor who's doing the video asks some really good questions. Okay. So cathode ray experiments were used to determine the ratio of an electron's charge to its mass. And so results showed that the mass of the charged particle was much less than a hydrogen atom, which was the lightest known atom at the time. Dalton had been incorrect. Remember, he said atoms were indivisible. Atoms are divisible into smaller subatomic particles. Difference is, once you get to those subatomic particles, then the atom loses its unique properties that make it an element. And so all atoms are made of 3 subatomic particles that were discovered through various experiments and methods. So J.J. Thomson identified electrons as a subatomic particle using those cathode ray experiments after Sir William Crookes originally found them. So he didn't use the mass to charge ratio to figure it out. J.J. Thomson did. So he helped us define the first subatomic particle. He also created our first model of the atom that wasn't just this whole ball of solid mass. And so J.J. Thomson said that the atom had a spherical shape, but it also had uniformly distributed positive charge, and then the negative electrons just kind of floated in it. If you've ever seen like a fruit cake or a plum pudding, it would be something like that, or even like the jellos where the fruit's suspended in it, and it's like distributed through the whole thing. Um, it just we call it the plum pudding model because plums are round. So it's the best analogy that we have. And so the plum pudding model was the first model where you had a subatomic particle in the atom. Now, the next experiment, which helped us identify the mass and charge even better, was Robert Millikan's oil drop experiment. He measured both the mass and charge using an oil drop apparatus. And so basically, what he did was he took an atomizer, this little perfume looking thing, and he sprayed droplets that were just oil droplets. And they dripped through this positively charged plate one at a time. The hole was only big enough for one droplet. And he looked through this telescope and he adjusted the charge between the positive and negative plate until he could stop the oil drops in midair. And so basically what he did was he used that charge that he had to counteract the force of gravity. And so he was levitating drops. In fact, if one of them got too much charge, it would actually start traveling upwards. And so by using that in the readout on his little gauge where he was adjusting that charge, he was able to measure that ratio of mass and charge. So just a quick recap, the 3 people that were most involved in the finding and defining of electrons were Sir William Crookes, J.J. Thomson, and Robert Millikan. Then Rutherford came along, and Rutherford's a pretty cool guy. He basically led this huge lab. A bunch of his like students had their own amazing like discoveries as well under his guidance, but he's responsible for finding out that there's a nucleus in the atom. So Rutherford wanted to know how positively charged alpha particles, which are a kind of radiation we'll talk about later, interacted with solid matter. So he would put a radiation source inside of a lead block, and it would shoot a beam of alpha particles at a gold foil. And then he had a zinc sulfide coated screen. And what this does is it lights up when the alpha particles hit it. So all its function is. And so he aimed the particles at the thin sheet of gold foil, and he expected the path of the alpha particles to only be kind of altered with collisions with an electron. But what he found out was some of the alpha particles did what he expected. They were deflected at a small angle. Most of the alpha particles, though, passed all the way through the foil with little to no deflection. And then some very small amounts of the alpha particles were deflected at a really large angle, which was completely unexpected because electrons don't have enough mass to deflect an alpha particle like that. So he immediately knew that there was something going on. And so since most of the alpha particles went through the gold foil, because a few of them bounced back at a very large angle, he knew that the plum pudding model was not right because it couldn't explain the results of his experiment. So he came up with a new model, and he's called it the nuclear model. And it says that the atom is a dense, positively charged nucleus surrounded by negative electrons, just like in this picture here. Now, one of the people who was studying underneath of Rutherford was James Chadwick. James Chadwick went further, and he wanted to know what was in the nucleus. And so he found that neutrons and the positively charged protons make up the nucleus of an atom. He says neutrons have no charge. It makes up the missing mass of the atom. They have the same mass as protons, and they're found in the nucleus of an atom. So Rutherford found the positive part of the nucleus, the protons. James Chadwick found the neutrons. The neutrons were much harder to observe because they're very non-reactive and having no charge. Okay. And so this example is Chadwick's model, where you show the black neutral neutrons, the red positive protons, and the the blue electrons. I'm sorry. And then the last model we're going to talk about is Schrodinger's electron cloud model. So if you've heard anything about philosophy, you might have heard Schrodinger's name before. He's the guy who's put the cat in the box, and he said, oh, we can't know if it's alive or if it's not alive until we open the box because we're not observing it. He actually used that as an analogy for observing electrons. And he proposed that we cannot know exactly where an electron is without changing its speed or location, simply because the way that we observe it would alter one of those two things. If we hit it with a beam of light, we're going to change its location because we're going to move it. And then if we try to measure it with some sort of like scanning electron microscope or anything like that, we're going to change its speed because we're going to slow it down with the radiation it's getting hit by. So he said the only thing we can do is predict the location in a cloud of probability, which is what this picture represents. The really dense areas are the high probability areas where you'll see an electron. The less dense areas are where it's less likely to be, and then the areas where there's just plain white is where it's not going to be at all. All right, we're going to wrap it up here. Check out the links that are with this video because they kind of help explain each of the models a little bit better as well, because they're just like they're extra material basically.